Hello everyone, and welcome to today's video lecture, which is on the Euler MacLaurin summation formula with the remainder term. And this remainder term actually wasn't known to Euler and Maclaurin when they derived the formula. They derived it as an infinite series that they would just truncate. The remainder term was actually discovered about a century later by the great French mathematician Poisson. And so this version of the Euler MacLaurin summation formula that we're deriving today is really the final or contemporary version of the formula as it's understood. So the agenda for today's video lecture is pretty straightforward. We're first going to derive the Euler MacLaurin summation formula with the remainder term, and then we're going to use it for an important application. We're going to use that version of the formula to estimate the Euler-Mascheroni Constant, which is denoted by gamma, and gamma equals the limit as n approaches infinity of the harmonic series, the sum from k equals 1 to n of terms 1 over k, minus the log of n. So it's the difference basically between the infinite harmonic series, which diverges, and the logarithm, which also diverges. But this difference actually has a finite value. It approaches a limit which is denoted by gamma, and that's an important constant that shows up all over mathematics. So let's just begin by reminding ourselves of the motivating idea that underlies the development of the Euler MacLaurin summation formula. And the idea is just this. Suppose that we have some function, y equals f of x, and we want to sum the values of that function on all of the integer values of x, the positive integer values of x, I mean, so f of 1 plus f of 2 plus f of 3 and so on. This function is very general. It's not completely general. I mean, we're requiring that the function is smooth and that it has as many derivatives as we need, but these are the kinds of functions that we work with in calculus. And then we know from calculus that the discrete summation of f of x on these integer values, for x, f of 1 plus f of 2 plus f of 3 plus ... and so on, all the way up to f of n minus 1 plus f of n, we know that that discrete summation is a rough approximation of the definite integral of the function f of x dx from 0 to n. And so the concept of the Riemann integral is to make those rectangles smaller and smaller and smaller and add up more and more and more of them, and that in the limit, adding up infinitely many of these tiny rectangles will give us the Riemann integral. So in a sense, the Riemann integral is the continuous summation of the values of the function f of x, in contrast to this discrete summation where we just add up the values of the function on the positive integers. And so the natural question emerges, is there a formula connecting the discrete summation of the values of the function, the sum from, say, k equals 1 to n of f of k, to the continuous summation of the function, the integral from 0 to n of the function f of x dx? And amazingly, the answer is yes, and that relationship is expressed by the Euler MacLaurin summation formula. So first recall from our previous videos on this formula that Euler and Maclaurin independently derived an early version of the formula to approximate the discrete summation of a function on its integer values in terms of the integral of the function and its derivatives of all orders. And that formula is the following. If we have some function f of x, and we let x be some positive integer and let the function capital S of x equal f of 0 plus f of 1 plus f of 2 plus f of 3 plus ... plus f of x minus 1 plus f of x, then that summation function s of x equals the indefinite integral of f of x dx minus 1 over 1 factorial times negative 1/2 times f of x plus 1 over 2 factorial times 1/6 times f prime of x minus 1 over 3 factorial times 0 times f double prime of x plus 1 over 4 factorial times negative 1 over 30 times f triple prime of x minus 1 over 5 factorial times 0 times f quadruple prime of x plus 1 over 6 factorial times 1 over 42 times the fifth derivative of f of x minus 1 over 7 factorial times 0 times the sixth derivative of f of x plus 1 over 8 factorial times negative 1 over 30 times the seventh derivative of f of x minus ... plus ... Now, some patterns in this formula will jump out at us right away, like the factorials and the fact that we continue to take higher order derivatives of f of x. But what about those coefficients in green? Well, it turns out that those numbers, those coefficients in green, are a very famous sequence called the Bernoulli numbers. And if you're interested in learning more about the Bernoulli numbers, just please see the other videos on my channel where I discuss them at length. But I just want to point out here that the Euler MacLaurin summation formula, as Euler derived it, is an infinite series, right? This formula just goes on and on and on. And if we wish to approximate the value of s of x, we would want to truncate it somewhere if f of x has infinitely many derivatives. And so the question becomes, where should we do that? Now, if you're not already very familiar with the Bernoulli numbers, you might be misled to believe that this really isn't a problem. In general, if we're working with convergent series, the more terms we add, the better the approximation gets. So the logic there would be that we can just add as many terms as we want to get as close an approximation as we want. But that's actually not how things work with the Euler MacLaurin summation formula. The Euler MacLaurin summation formula diverges as we add more and more terms because the Bernoulli numbers actually grow large very fast. Now, it might not look that way if we only sample, say, the first 10 Bernoulli numbers. In fact, it appears at first that the Bernoulli numbers are getting smaller. We have b sub 0 equals 1, b sub 1 equals negative a half, b sub 2 equals 1/6, and then we have all the odd index Bernoulli numbers after b sub 1, b sub 3, b sub 5, b sub 7, and so on. Those all equal 0. And then we have b sub 4 equals negative 1 over 30, b sub 6 equals 1 over 42, b sub 8 equals negative 1 over 30 again. And then we have b sub 10, which is 5 over 66. Not really clear what direction this is going. But then look what happens when we have b sub 12. That equals negative 691 over 2,730. b sub 14 doesn't look too bad, that's just 7 over 6. But then b sub 16 is negative 3,617 over 510. b sub 18 is 43,867 over 798. b sub 20 is negative 174,611 over 330. b sub 22 equals 854,513 over 138. And so we can see, even without actually doing the division and reducing these fractions, that the Bernoulli numbers are getting larger and larger and larger, just by dint of the fact that the number of digits in the numerator of all of these terms is strongly outstripping the number of digits in the denominator. So what's actually going on here? Well, what's often the case is that when we're using the Euler MacLaurin summation formula to approximate the discrete summation of a function, often the first few terms get us close to the true value of the sum. But then as we add more and more terms, the Euler MacLaurin summation formula begins to diverge. As I mentioned, the Bernoulli numbers grow quite large in magnitude very quickly, and so that will cause the sum to either diverge in one direction or the other very quickly, often, or it'll cause the sum to oscillate wildly. So here's a visual representation of what that would look like. We can chart on the y-axis the sum of the terms in the Euler MacLaurin summation formula, and I've labeled the abscissa of this graph n for the number of terms in the formula, not for the number that we're summing up to. And then there's some true sum, some true value that the sum of the terms equals. I've labeled that s of x, and that can just be designated by this horizontal purple line. And what we see is that as we add up more and more terms in the Euler MacLaurin summation formula, initially the sum is getting closer and closer to the true value, to s of x. But as we keep adding terms, because the Bernoulli numbers grow bigger and bigger, the sum starts oscillating wildly around the true value. Well, Euler was aware of this problem with his formula, but a true quantitative solution eluded him. He just wrote that we should stop summing up terms in the Euler MacLaurin summation formula right when the formula starts to diverge. Well, that's a little bit too vague. We'd like to know very precisely how many terms can we add up to get as close as possible to the true value that we're interested in. And once we truncate our series, we'd like to also be able to bound the error so we know exactly how close we are. Now, as I've already mentioned, this remainder term or error term was not discovered until 1823 by Poisson. And so what follows in this video lecture, we'll rederive the Euler MacLaurin summation formula with Poisson's error term. And so we're going to begin this derivation by considering the function y equals f of x. And purely for reasons of visual simplicity, I've drawn f of x as a positive function. All the y values of this function are positive. And I've also drawn it as a constantly decreasing function. But neither of those assumptions is necessary for this derivation. It just helps keep things simpler visually. I also want to give proper credit in this video by mentioning that I'm largely following a derivation which is offered in Tom M. Oppesol's excellent article, An Elementary View of Euler's Summation Formula. So without further ado, here's our function. And what we want to do is consider the difference between the summation of the values of this function on the positive integers. So the sum of values f of k from k equals 1 to some value n minus 1. You can think of this as a very rudimentary right-sided Riemann sum. So this is f of 1 plus f of 2 plus f of 3 plus dot 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 all the way up to plus f of n minus 1, where n of course is an integer. We want to consider the difference between that sum and the definite integral from 1 to n of the function f of x dx. And we know, of course, that this definite integral can be represented by the area under the curve f of x. And so in this picture, the difference between those two areas is going to be represented geometrically by the sum of the areas of all the curvilinear wedges that are sitting above f of x, which I've outlined here in red. And let's call the sum of these areas d sub n. And so d sub n equals this difference. It equals the difference between the summation of f of k from k equals 1 to k equals n minus 1 minus the integral from 1 to n of f of x dx. Or equivalently, the sum from k equals 1 to n minus 1 of f of k equals the integral from 1 to n of f of x dx plus dn. So I'll bring that formula up to the top of the screen here, but now I just want to focus on one small piece of this picture. I just want to focus on the rectangle based at x equals k, so this is just some general value for x, which I've labeled as k. It's based from the point k to k plus 1, so it has a base width of 1, and the height of the rectangle is just f of k. So let me just kind of zoom in on this particular rectangle. Of course, it's a general rectangle based at x equals k. And what I'm particularly interested in is the difference between the area of this one rectangle and the area under the curve y equals f of x from x equals k to x equals k plus 1. So the difference between those two areas is just, of course, this curvilinear wedge, which is a tiny piece of dn. So let me just make this picture a little bit bigger. Again, we have our rectangle based at x equals k. It has a height f of k. And the area that we're interested in, the area of this curvilinear wedge, which is a piece of dn, is equal to the value f of k minus the integral from k to k plus 1 of f of x dx. And I know I'm throwing a lot of terms at you here, but it actually helps us keep track of everything. Let's call the area of this single curvilinear wedge, let's call that area I of k. And with that notation in mind, we can return to our big picture, where we have the formula that the sum of the values of f of k from k equals 1 to k equals n minus 1 is equal to the integral from 1 to n of f of x dx plus dn. But now with our new terminology for the individual pieces of dn, we can write that this sum equals the integral plus I of 1 plus I of 2 plus dot 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 plus I of k plus dot 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 plus I of n minus 1. Well, we can simplify this expression by writing that this sum equals the integral from 1 to n of f of x dx plus the sum of the values of I of k from k equals 1 to k equals n minus 1. And then substituting back in our definition for I of k, we have that the sum of the values of f of k from k equals 1 to k equals n minus 1 equals the integral from 1 to n of f of x dx plus the sum from k equals 1 to k equals n minus 1 of f of k minus the integral from k to k plus 1 of f of x dx. So I'll just move that expression to the top line here, and now I just want to focus on the second part of the right-hand side of the equation, that sum of the difference between f of k minus the integral from k to k plus 1 of f of x dx. And it might be easier to evaluate that difference if we consider it as just one integral. And to do that, we have to have the key insight. which is that f of k itself can be expressed as an integral. Namely, f of k equals the integral from k to k plus 1 of f of k dx, not f of x dx, f of k dx. Now, why does that work? It works because f of k is itself just a constant. Remember, k is just some fixed value, not a variable here, which means that the integral equals, I can pull the constant out, f of k times the integral from k to k plus 1 of 1 dx. So we get that this equals f of k times x evaluated from k to k plus 1. That equals f of k times the quantity k plus 1 minus k, which of course just equals 1. And so we end up with f of k. And so now I can rewrite this sum on the right-hand side as the sum from k equals 1 to k equals n minus 1 of, open parenthesis, the integral from k to k plus 1 of f of k dx minus the integral from k to k plus 1 of f of x dx, close parenthesis. And then I can combine those two integrals into one. So I'll get that this equals the sum of the integrals from k to k plus 1 of f of k minus f of x dx. Now, this integral expression is actually very important for what we're trying to do here. It essentially captures the discrepancy between the discrete summation of the function on the left-hand side and the continuous summation of the function on the right-hand side. So we need to focus on this a little bit more carefully now. Now, we want to see what we can do with this integral. And this might not be the most natural idea, but it actually leads us where we want to go. We can rewrite the expression by performing integration by parts. And you'll recall integration by parts takes an integral of the form u dv, and it rewrites that integral. So here I'm going to set u as f of k minus f of x, the expression f of k minus f of x. And then for dv, I'm going to write 1 dx. I'm putting that 1 there, although it might seem superfluous, because it's going to show up in integration in a moment. And now I'm just going to ask you to recall what we do in integration by parts, which is to rewrite the integral of the form, the integral from a to b of u dv. We rewrite that integral as u of x times v of x evaluated from a to b minus the integral from a to b of the function v du. So we have u of x equals f of k minus f of x, and then when we differentiate with respect to x, we have du dx equals 0. Remember, f of k here is a constant, so when we differentiate it, we just get 0, minus f prime of x. Therefore, du equals negative f prime of x dx. So I'll just write those facts on the right-hand side of the screen here. And now we want to consider what happens with dv. Well, we have dv equals 1 dx. So when I integrate both sides, you get the integral of dv equals the integral of 1 dx. Therefore, v equals x plus some constant of integration c. Now, often we just ignore the value c because when we do integration by parts, that constant c gets canceled out when we compute u of x times v of x evaluated from a to b. The constant just gets subtracted out. But this is an abstract derivation, and we're free to consider any value of c that we want. We're not forced by the problem to arrive at some particular value of c. So I want to leave c in and consider what value it could take. So let's see what happens when we let c, the constant c, equal the negative of the quantity k plus 1. So v equals x plus c, therefore v equals x minus the quantity k plus 1. So I'll move those facts to the right-hand side also, and now let's use these facts to actually do this integration by parts. So again, we have, by our formula for integration by parts, that the integral from a to b of u dv equals u of x times v of x, evaluated at the endpoints a and b, minus the integral from a to b of v du. So here we'll have u of x is the expression f of k minus f of x, and we'll put that there in parentheses, and that's multiplying v of x, which we have determined to be x minus what we set our constant to be, minus k plus 1 there, evaluated at the endpoints, evaluated from k to k plus 1, minus the integral, this is the v du integral, from k to k plus 1 of v, that's going to be, again, x minus the quantity k plus 1, close parenthesis, times du, which is, again, negative f prime of x dx. So now I'm going to erase some of that material on the right-hand side there so that I can get this expression all on one line. And now let's see why setting our constant c to the value negative, open parenthesis, k plus 1, close parenthesis, why that's such a good idea. Well, when we evaluate the expression u of x times v of x at our endpoints k and k plus 1, we get the expression f of k minus, now substituting in k plus 1 for x, minus f of k plus 1, close parenthesis, times the expression, again plugging in k plus 1 for x, k plus 1, minus the quantity k plus 1. That's going to be when we set x equal to k plus 1. And then we subtract from that u times v when we set x equal to k. And there we'll have this equals f of k minus, plugging in k for x here, f of k, times the quantity k minus k plus 1, close parenthesis. And then we have the rest of our expression here that's minus the integral from k to k plus 1 of v du, which is x minus the quantity k plus 1 times negative f prime of x dx. I'm just going to take that double negative and change it to a positive sign, so this will be plus the integral. And now, because of our very clever choice of letting c equal negative the quantity k plus 1, we get to make some wonderful cancellations here. So on the left, I have f of k minus f of k plus 1 multiplying 0. And on the right, I have f of k minus f of k, which of course is 0, multiplying k minus k plus 1. So those terms both equal 0. And the only term that's left from this integration by parts is plus the integral from k to k plus 1 of the quantity x minus the quantity k plus 1, close parenthesis, times f prime of x dx. So now we have that the integral from k to k plus 1 of the quantity f of k minus f of x dx equals the integral from k to k plus 1 of the quantity x minus, open parenthesis, k plus 1, close parenthesis, times f prime of x dx. So it might not seem at first that doing this integration by parts has really advanced things very much for us, but something amazing is about to happen. We're going to be able to write this entire integral purely in terms of x. And let's see why that is. If we look at the integrand, we have the expression x minus the quantity k plus 1. Well, that's equivalent to writing the quantity x minus k minus 1. And now if I look at x minus k very closely, the relationship between x and k isn't arbitrary. K is an integer, and in fact on this interval from k to k plus 1, as x ranges in values from k to k plus 1, k is equal to the floor of x, the greatest integer less than x. And so we note that by putting brackets around x. So instead of writing x minus k, I'm going to write x minus the floor of x minus 1. So because that step is so important, I'm going to show it again. We have from integration by parts that the integral from k to k plus 1 of the expression f of k minus f of x dx equals the integral from k to k plus 1 of the expression x minus the quantity k plus 1 all times f prime of x dx. And by rearranging negative signs, that equals the integral from k to k plus 1 of the quantity x minus k minus 1 all times f prime of x dx. But then again, on this interval, k is just the floor of x. So that expression equals the integral from k to k plus 1 of x minus the floor of x minus 1 all times f prime of x dx. And now we have that integral purely in terms of x. So now that we've done all that work on this integral, we can sub it back into our formula. So we have that the sum of the values of f of k from k equals 1 to k equals n minus 1 equals the integral from 1 to n of f of x dx plus, and now I'm going to rewrite this sum. This is the sum from k equals 1 to n minus 1 of the integral from k to k plus 1 of the quantity x minus the floor of x minus 1 all times f prime of x dx. And now the beauty of this expression is that we can sum all of these integrals together. So that means that the sum of all the values of f of k from k equals 1 to n minus 1 equals the integral from 1 to n of f of x dx plus, and now I'm going to sum all of these individual integrals together into one big integral. And here I have to be careful about the boundaries. This will be the integral from 1 to n minus 1 plus 1, right? Because each of the individual integrals is integrating from k to k plus 1. So when I substitute in n minus 1 for k, I get n minus 1 plus 1, but that just works out to n. So this is the integral from 1 to n of the expression x minus the floor of x minus 1 all times f prime of x dx. But I can actually clean up that integrand a little bit more, that expression x minus the floor of x minus 1 all times f prime of x dx. A more natural way to write this integral would be to distribute the f prime of x across the quantities x minus the floor of x and negative 1 and just split it up. And so then we'll have that integral equals the integral from 1 to n of the quantity x minus the floor of x times f prime of x, and then distributing the f prime of x to multiply the negative 1, that'll be minus the integral from 1 to n of f prime of x dx. And what's so great about writing the equation that way is that last term, minus the integral from 1 to n of f prime of x dx, that's super easy to integrate. The integral of f prime of x is just f of x, so that integral will equal minus f of x evaluated at the endpoints 1 and n. So this expression, that last term, will be minus the quantity f of n minus f of 1, close parenthesis. So I'll move that equation to the top here and distribute the negative sign, so those last two terms will be minus f of n plus f of 1. And now I'm going to add f of n to both sides of the equation. So when I do that, the f of n will cancel out on the right-hand side, and the left-hand side of the equation will be the sum of the values of f of k from k equals 1 to n minus 1 plus f of n. But then, of course, I can combine that f of n into the sum. And when I do that, I'll have that the left-hand side equals the sum from k equals 1 to n of f of k. And note now on the right-hand side of the equation, the bounds of my integrals are also both from 1 to n. So that's very pretty now. And so now we have the beautiful expression that the sum of the values of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus the integral from 1 to n of the quantity x minus the floor of x, close parenthesis, times f prime of x dx plus f of 1. Now let me just rearrange these terms on the right-hand side because I really want to focus on that integral that we just developed. Now I could be even more concise in the way that I've written this integral on the right-hand side, because that expression in the integrand, x minus the floor of x, that's really just what we can call the fractional part of x. Because if we take x, some value x, and we subtract off of it the greatest integer less than x, we're going to be left with some fractional number whose value is going to lie between 0 and 1. So we need some new notation for this concept. We'll call x surrounded by the curly braces the fractional part of x. And so this expression, the fractional part of x, which is equal to x minus the floor of x, that's multiplying f prime of x in the integrand. And we can actually graph the function y equals the fractional part of x to get a better idea of what that function looks like. So I can put down some coordinate axes here, and I'll just mark off a few points on the x-axis, and let's try to graph the function y equals the fractional part of x. Well, initially this function, if we're just starting with the positive values for x, initially this function looks a lot like y equals x. When x equals 0.1, y equals 0.1. When x equals 0.5, y equals 0.5. But as soon as x equals 1, the fractional part of x equals 0, right? The value of the y coordinate just drops right back down to 0. And then it starts increasing again along a line parallel to the line y equals x. So when x equals 1.1, y equals 0.1. When x equals 1.5, y equals 0.5. When x equals 1.9999999, y equals 0.9999999. And as soon as x equals 2, wham, the function drops back down to 0 again, the y value I mean. And that process repeats itself. So this is actually a periodic function. It has a period of 1. And so that's what the function looks like, the function y equals the fractional part of x, which in our integral as it's written is multiplying f prime of x. So what is this equation saying? It's saying that if I want to find the sum of all the values of f of k from k equals 1 to n, I take the integral from 1 to n of f of x dx, I add to that the value f of 1, and then I add to that this strange beast of an integral where I'm multiplying the fractional part of x by f prime of x. That seems like it's going to yield a fairly large error. I have to keep multiplying f prime of x by these values that fluctuate between 0 and 1 again and again and again all the way up to n. That doesn't seem like a very easy integral to deal with. And in fact, the form in which our summation formula is currently written, even though it's very concise and even elegant, it's not at all useful. Because what is this formula really saying here? It's saying that the discrete summation of the function f of k from k equals 1 to n equals the continuous summation of the function, the integral from 1 to n of f of x dx, plus f of 1, plus this weird integral that looks like it's going to be difficult to evaluate and also looks like it might be rather large. But let's not lose hope here, because we can make that final integral, which I'm calling the error integral, we can make that integral smaller if we shift the fractional part of x down by 1/2. So let me show you what that would look like. We're going to shift the entire graph down by 1/2, so our new function is going to be y equals the fractional part of x minus 1/2. And so it'll be identical to y equals the fractional part of x, but everything is shifted down by 1/2. And now something wonderful happens. The function changes sign with every single oscillation. It starts at negative 1/2 and it ends at positive 1/2. Then it drops back down to negative 1/2 and it goes all the way up to positive 1/2. And our expectation is that because the function is changing signs with every oscillation, when we multiply it by f prime of x, because of all the sign changes, some cancellations will happen within the integral, and the error integral will be smaller. So the function y equals the fractional part of x minus 1/2, that equals x minus the floor of x minus 1/2. And again, we want to get that expression into the integral. I would much rather have a function that changes sign with every oscillation, multiply f prime of x, than a function whose sign is always positive. Well, how can we make that happen? We can do it by using a little accounting trick inside our integral. We're going to rewrite the integral as the integral from 1 to n of x minus the floor of x minus 1/2 plus 1/2, close parenthesis, and that expression minus 1/2 plus 1/2, of course, that just equals 0. So I haven't actually changed the value of the integral. I've just rewritten it in a clever way. But now with that clever trick of adding 0 inside the integrand, I actually now have this integral in more workable form, because I can split off that part of it, the plus 1/2 inside parenthesis, and rewrite the integral as the integral from 1 to n of x minus the floor of x minus 1/2 times f prime of x dx plus the integral from 1 to n of 1/2 times f prime of x dx. And of course that last integral there, the integral from 1 to n of 1/2 times f prime of x dx, that's very easy to evaluate. That's just 1/2 times f of x evaluated from 1 to n, which equals 1/2 times the quantity f of n minus f of 1. So I'll write that there in place of the integral 1/2 times the quantity f of n minus f of 1, but I already have a plus f of 1 in this equation. So I have plus f of 1 minus 1/2 f of 1. That's just going to give me a plus 1/2 f of 1 for that term there. So my final form of this equation is that the sum of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus 1/2 times f of 1 plus 1/2 times f of n plus the integral from 1 to n of x minus the floor of x minus 1/2 all times f prime of x dx. But I want to just rewrite those two terms in the middle, 1/2 times f of 1 plus 1/2 times f of n. That's really the average of f of 1 and f of n if I combine those two terms together. It's f of 1 plus f of n over 2. And some people call this term in the formula the trapezoidal correction term because it's the trapezoidal height that we would use if we were estimating the integral by the trapezoid rule. So there's our trapezoidal correction term. And now I want to put a box around this equation, and I'll move it to the top of the screen. This is a very important result for this video, and it's really our most basic form of the Euler MacLaurin summation formula. It says that the sum of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus the average of the values of f of x at the endpoints plus the integral from 1 to n of x minus the floor of x, which just equals the fractional part of x, minus 1/2 all times f prime of x dx. And we call this equation the first derivative form of the Euler MacLaurin summation formula with remainder term. And while that's great, we don't necessarily want to stop there, and we can actually expand this formula further by evaluating that final error integral term. And to do that, we're going to have to give a little bit more thought to how to integrate functions of the fractional part of x. And so to do that, let's start with the simplest possible case. We're going to consider a general integral from 0 to some value t of the function fractional part of x dx. And so I'll just draw my coordinate axes here, x and y, and I'll just mark off a few points on the x-axis, 1, 2, 3, ... all the way up to some integer n, and then finally we'll have our value t that doesn't necessarily need to be an integer. In fact, I'll make that point explicit by drawing t between n and the next tick mark, which would represent the integer n plus 1. And now I can graph the function y equals the fractional part of x, and the integral from 0 to t of the fractional part of x dx is just going to equal, as it always does, the area under the function, the area bounded by the function and the x-axis, from x equals 0 to x equals t. But this area is actually easy to compute, because what we have here is just n triangles, n isosceles triangles, with a base of 1 and a height of 1, and so each of these triangles has an area of 1/2 times 1 times 1, or just an area of 1/2. So n times 1/2, that gives us an area of n over 2, and then we just have to account for the area contributed by the piece of the integral from n to t. So that's the integral from n to t of the fractional part of x dx. But due to the periodic nature of the function y equals the fractional part of x, that area represented by the integral from n to t of the fractional part of x dx is exactly equivalent to the integral from 0 to the point t minus n of the fractional part of x dx. But what is n equal to here? Well, n is the greatest integer less than t. In fact, n is equal to the floor of t. And that means that t minus n equals t minus the floor of t, which equals the fractional part of t. So this integral is actually equal to the area. Instead of writing n over 2, I'm going to write floor of t over 2, plus the integral from 0 to, instead of t minus n, I'm going to write fractional part of t of the fractional part of x dx. And so that means the entire integral, the integral from 0 to t of the fractional part of x dx, equals the floor of t over 2 plus the integral from 0 to the fractional part of t of the fractional part of x dx. But on the interval from 0 to 1, the fractional part of x just equals x. So I can actually revise this integral to say that it equals the floor of t over 2 plus the integral from 0 to the fractional part of t of x dx. Well, that's an integral we know how to compute. So this entire integral is going to equal the floor of t over 2 plus x squared over 2, evaluated at the endpoints 0 and fractional part of t. So this is going to equal floor of t over 2 plus the fractional part of t squared over 2 minus 0 squared over 2. So again, we get that the integral from 0 to t of the fractional part of x dx equals the floor of t over 2 plus the fractional part of t squared over 2. So I'll write that formula on the upper right part of the screen there and put a box around it because we'll come back to that result again. But now I want to take the analysis that we've just done and generalize the result for integrals of the type integral from 0 to t of the fractional part of x to some exponent k dx. And again, I'll draw a generalized sketch of what that function would look like. And once again, I'll tick off some integer values on the x-axis, 1, 2, 3, ... all the way up to some integer n. And then we'll have our value t, which is going to lie between the integers n and n plus 1. And then our function y equals the fractional part of x to the k, that will just be a periodically repeating curve, a concave upward curve. So this curve could represent the first part of a parabola from 0 to 1, or the first part of a cubic from 0 to 1. But whatever it is, it's going to represent that repeating segment of the graph of, for example, the function y equals x squared from x equals 0 to 1, or y equals x cubed from x equals 0 to 1, or y equals x to the fourth from x equals 0 to 1, and so on. And once again, this integral will be represented by the area bounded between the function y equals the fractional part of x to the k and the x-axis between x equals 0 and x equals t. And so what that means for us is that we'll have n copies of areas equal to the integral from 0 to 1 of x to the k dx, which equals n times x to the k plus 1 all over k plus 1, evaluated at the endpoints 0 and 1. So that equals n times the quantity 1 to the k plus 1 over k plus 1 minus 0 to the k plus 1 over k plus 1, and that just equals n over k plus 1. So that's the easy part. That piece of the integral equals n over k plus 1, and then the rest of the integral is just the integral from n to t of the fractional part of x to the k dx. And so once again, n equals the floor of t, so I can replace n with floor of t in that expression. And then the integral from n to t of the fractional part of x to the k dx, that's going to be equal to the integral from 0 to t minus n of the fractional part of x to the k dx, which equals 0 to the fractional part of t of the function x to the k dx, so that will equal x to the k plus 1 over k plus 1 from the fractional part of t to 0, which equals the fractional part of t to the k plus 1 over k plus 1. So now we can compute the entire integral. The integral from 0 to t of the fractional part of x to the k dx equals the floor of t plus the fractional part of t to the k plus 1 all over k plus 1. Okay, so now that we know how to integrate the fractional part of x to the k dx, let's use these results to refine our Euler MacLaurin summation formula. So let's go back to our first derivative form of the Euler MacLaurin summation formula, which says that the sum from k equals 1 to n of f of k equals the integral from 1 to n of f of x dx plus f of n plus f of 1 all over 2, plus the integral from 1 to n of the quantity fractional part of x minus 1/2, close parenthesis, times f prime of x dx. So we need to do a little bit more work on this integral term here, and we'll use what I hope is by now a familiar technique. We'll use integration by parts. And so when we do that, we treat the integral as if it's of the form u dv. Here I'm going to let u equal f prime of x, and dv is going to be the fractional part of x minus 1/2 dx. So therefore, if u is f prime of x, then du dx is f double prime of x, which means du is f double prime of x dx. And then we have that dv equals the quantity fractional part of x minus 1/2, close parenthesis, dx. And we have to find v by integrating that expression. But we know how to do that because we've already put in the work. We showed that the integral from 0 to t of the fractional part of x dx is equal to the floor of x plus the fractional part of x squared all over 2. So we can then conclude that v equals the floor of x plus the fractional part of x squared all over 2 minus, now just integrating the constant here, minus 1/2 times x. But remember, the floor of x is just equal to x minus the fractional part of x, so I can rewrite this expression as x minus the fractional part of x plus the fractional part of x squared all over 2 minus 1/2 x. And so then I have an x over 2 and a minus 1/2 x. Those terms cancel. So I'm just going to write this more neatly now as v equals the fractional part of x squared minus the fractional part of x all over 2. And I'll just move that fact to the right here. And so now we're actually ready to do this integration by parts. And recall, integration by parts is the formula that says the integral of the expression u dv equals u times v minus the integral of v du. So for u times v, we have f prime of x, that's u, times the expression fractional part of x squared minus the fractional part of x all over 2, that's v, evaluated at the endpoints from 1 to n, minus, and now here's the integral v du, the integral from 1 to n of v, that's fractional part of x squared minus fractional part of x all over 2, times du, which is f double prime of x dx. But now something really great happens in our first term of this integration by parts. At integer values, the endpoints 1 and n, the fractional part of x equals 0. So this entire term just cancels out. It equals 0. And so we're left with this integral equaling, here I'll just factor out the 2 in the denominator there, equaling negative 1/2 times the integral from 1 to n of open parenthesis, fractional part of x squared minus the fractional part of x, close parenthesis, times f double prime of x dx. Now it would be great if we were done here and we had a new form of the Euler MacLaurin summation formula, but this current equation as it's written is really not that different in principle from our equation that we started with. We have the summation of the values of the function discretely on the left-hand side, And that's going to be equal to the integral from 1 to n of f of x dx, plus the average of the values of f of x at the endpoints. And then we've now subtracted off this new integral. So this new equation isn't really giving us much more new information, really. So we need to do a little more work on this integral. And we can do that by doing another round of integration by parts, which is actually a common strategy. If one round of integration by parts doesn't get you the answer, do another round. So we want to evaluate the integral from 1 to n of, open parenthesis, fractional part of x squared minus the fractional part of x, close parenthesis, times f double prime of x dx. And once again, I'll flip those two terms around and write them as u dv, so I'll make u f double prime of x, and dv will be the other expression. And so we'll have u equals f double prime of x, du equals f triple prime of x dx. And to find v, we'll want to integrate the expression fractional part of x squared minus fractional part of x dx. But recall, we already found that the integral from 0 to t of the fractional part of x to the k dx equals the floor of x plus the fractional part of x to the k plus 1 all over k plus 1. So we can use that fact here and find that v equals the floor of x, I'm integrating the fractional part of x squared first, the floor of x plus the fractional part of x cubed all over 3, and now I'll integrate the fractional part of x, minus the floor of x plus the fractional part of x squared all over 2. And now this equals, translating floor of x into x minus fractional part of x, this equals x minus the fractional part of x plus the fractional part of x cubed all over 3, minus x minus the fractional part of x plus the fractional part of x squared all over 2. Then if we simplify and combine terms, we get that v equals negative x over 6 plus the fractional part of x over 6 minus the fractional part of x squared over 2 plus the fractional part of x cubed over 3. So I'll move that result over to the upper right here. And now when we try to actually do this integration, things are not going to work out so beautifully. But don't worry, this is salvageable. I just want to show you what the computation would look like if we were not to make the necessary correction we're about to make. We would have uv, so we'd have f double prime of x times that expression v, I'm not going to repeat it there, evaluated from n to 1, minus the integral of v du, which is the integral of our expression v again, multiplying f triple prime of x dx. And here's where we run into trouble. You see that in the uv term of that integration, in our previous round of integration by parts, that term canceled. You can look back and see that we had f prime of x multiplying terms that only contained the fractional part of x. But here we have a negative x over 6. That's a non-fractional negative x over 6. So at the endpoints, that term is not going to equal 0. And so the uv in this integration is not going to cancel. And that makes us sad. We need to fix that. Similarly, in our integral v du, again we have that non-fractional negative x over 6. Remember that we're thinking of this integral as the remainder after we approximate the summation of the function on the left-hand side with all the other terms in the Euler MacLaurin summation formula. Being non-fractional, it's going to make our integral larger than we want. And so we need to figure out some way to get rid of this negative x over 6 term in the integration. But before I show you how we do that, let's just pause for a second to review what we've considered so far. First, we derived the first derivative form of the Euler MacLaurin summation formula, namely that the summation of the values of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus the quantity f of 1 plus f of n over 2 plus this remainder integral, the integral from 1 to n of, open parenthesis, fractional part of x minus 1/2, close parenthesis, times f prime of x dx. We then performed integration by parts on this integral to obtain an intermediate formula. That formula for the summation of the values of f of k from 1 to n had the same first two terms in it on the right-hand side, but then with this new integral, minus 1/2 times the integral from 1 to n of the fractional part of x squared minus the fractional part of x, close parenthesis, times f double prime of x dx. But as I mentioned before, this new integral doesn't seem to be telling us a whole lot that's new. So we attempted integration by parts on that integral again, and we then obtained the following. Okay, before I write that, let me just move everything up here to make a little bit more room. And let me actually put a box around the first derivative form of the EMSF so that we don't lose track of that formula. Okay, returning to the main line of the argument, we did this integral, and we got this ugly beast of an expression, and I'm calling it an ugly beast because it has these non-fractional terms in it, negative x over 6 in the uv term, and again, a negative x over 6 in the integrand of the VDU term. And the question before us is, can we do anything to fix that integral to get rid of these negative x over 6 terms? And the answer is actually yes. We saw this trick already once before. What we're going to do is rewrite the integral fractional part of x squared minus fractional part of x close parenthesis times f double prime of x dx. We're going to rewrite that integral without changing its value as the following. Here I'll just move it over to the left to make some room, and now I'm also going to make a space between the first term, fractional part of x squared minus fractional part of x, and that second term it's multiplying f double prime of x, because I'm going to rewrite that first term in the integrand as fractional part of x squared minus fractional part of x plus 1 over 6 minus 1 over 6, and then close parenthesis times f double prime of x dx. And by doing that, I've effectively added 0 inside that term of the integrand. So I've changed the form of the integrand without actually changing its value. But here's why doing that is such a great idea. Once I make that cosmetic change to the integrand, I can break the integral into two separate pieces. The first piece will be fractional part of x squared minus fractional part of x plus 1/6, close parenthesis, times f double prime of x dx. And then the other integral will be plus negative a half, because there's a negative 1/2 outside this integral, right? Times the integral from 1 to n of negative 1/6 times f double prime of x dx. I'm basically applying the distributive law there and breaking the integral into two pieces. And now, because I've rewritten the integral this way, something really nice happens. When I do integration by parts, not much changes. I'm still going to call u f double prime of x, and I'm still going to make dv the fractional part of x squared minus the fractional part of x, but now I'm also going to include in dv that plus 1/6, that's a constant term. So when I do the integration by parts and I integrate dv, the computation is identical, so I'm not going to take you through it again. We get the same thing, minus x over 6 plus the fractional part of x over 6 minus the fractional part of x squared over 2 plus the fractional part of x cubed over 3. But now we also bring along this additional term, plus 1/6 x, which comes from integrating the constant term 1/6. And that plus 1/6 x also shows up in the integral of v du, so I'll write it there. And then, of course, we still have to do the integration that we split off, the negative 1/2 times the integral from 1 to n of negative 1/6 times f double prime of x dx. And now, because we took the trouble to effectively add 0 inside the integral, adding a sixth and subtracting a sixth and then splitting the integral up, something very nice happens in our integration. The negative x over 6 term, which was causing us so much grief, is actually canceled out by the plus 1/6 x. And because, again, the fractional part of x equals 0, at the boundaries where it's being evaluated, at the integer values 1 and n, that whole term v equals 0, so we get f double prime of x times 0, so that entire uv expression just cancels away. And the only term left in this integration by parts, the integral of v du, well, that integral also looks somewhat better because negative x over 6 is canceled out by plus x over 6 in v. And so we're left with an integral that only contains terms in the fractional part of x. And remember, this is our remainder integral, so because it now only has fractional part of x terms in it, we expect that this remainder integral is going to be significantly smaller. But something else really nice happens as a result of adding 0 inside the integral in a clever way. We already talked about what happens when we add 1/6. We get all of those nice cancellations from the integration. But remember that we also had to break off a small piece, the minus 1/6 times f double prime of x dx, and that carries the coefficient in front of it, the negative 1/2. So we need to evaluate that integral, minus 1/2 times the integral from 1 to n of minus 1/6 times f double prime of x dx. But as it happens, that integral is really easy to evaluate. That integral would equal, well, we have a double negative there, so that becomes a positive, and we get plus I'll switch around the order of the coefficients here, plus 1/6 times f prime of n minus f prime of 1 all over 2. And so we get that in both of these equations here. So I'm just going to rearrange those terms so that the final term in both of these equations is the remainder integral in different forms. And now, as a result of that one trick of adding 0 inside the integrand to make cancellations, we've now actually arrived at two new versions of the Euler-Maclaurin summation formula. The first one up top that I put a box around is known as the second derivative form of the Euler-Maclaurin summation formula with remainder, because it contains f double prime of x in the remainder integral. And the equation below that is known as the third derivative form of the Euler-Maclaurin summation formula, because it contains f triple prime of x in the remainder integral. So we now have three versions of the Euler-Maclaurin summation formula with remainder term. Let's line these up and see if there are any interesting patterns. Well, for our first derivative form of the EMSF, we have that the summation of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus the average of f of n and f of 1, so that's f of n plus f of 1 all over 2, plus this remainder integral, the integral from 1 to n of, open parenthesis, fractional part of x minus a half, close parenthesis, times f prime of x dx. For our second derivative form of the EMSF, our first two terms on the right-hand side are exactly the same as the ones in the first derivative form, but then we have this new term, this plus a sixth times f prime of n minus f prime of 1 all over 2. And then we have a new remainder integral, which is minus a half times the integral from 1 to n times, open parenthesis, fractional part of x squared minus fractional part of x plus 1/6, close parenthesis, times f double prime of x dx. And then we have the third derivative form of the EMSF, and its first three terms are the same as the terms on the right-hand side of the second derivative form of the equation, but the error integral is different. Our error integral is plus 1/2 times the integral from 1 to n of, open parenthesis, fractional part of x cubed over 3, minus the fractional part of x squared over 2, plus the fractional part of x over 6, close parenthesis, times f triple prime of x dx. And now I want to just make a quick cosmetic change to this integral. I'm going to multiply that middle term, fractional part of x squared over 2. I'm going to multiply it by 3 over 3 so that I can then factor out a 1/3 from all of the terms. And then when I do that, I get that the integral equals plus 1/6 times the integral from 1 to n of fractional part of x cubed minus 3 times the fractional part of x squared over 2 plus the fractional part of x over 2, close parenthesis, times f triple prime of x dx. And now, having written out the first few forms of the Euler-Maclaurin summation formula with remainder term, we might notice an incredible pattern here, which is that the polynomial expressions inside the remainder integrals are not just ordinary polynomials. They're in fact very special polynomials called Bernoulli polynomials. And these polynomials are intimately connected with the Bernoulli numbers. In fact, we can think of them as a generalization of the concept of Bernoulli numbers. And so if you're at all interested in learning more about these polynomials and their amazing properties, I would encourage you to watch my previous video on this topic. So to review, we have that b1 of x, the first Bernoulli polynomial, equals x minus 1/2. And we see something similar to that in the first derivative form of the EMSF in the remainder integral. Our second Bernoulli polynomial, b2 of x, equals x squared minus x plus 1/6, and we see a version of that in our second derivative form of the EMSF. And then b3 of x, the third Bernoulli polynomial, equals x cubed minus 3/2 x squared plus x over 2. But note that in the remainder integrals of the various forms of the Euler-Maclaurin summation formula that we've derived here, we don't have Bernoulli polynomials in x, we have Bernoulli polynomials in the fractional part of x. And for reasons that will be clear in a moment, we give these polynomials a special name. We call them the periodic Bernoulli polynomials. And I think we can best appreciate why these functions are called periodic Bernoulli polynomials by looking at their graphs. So I'm going to do that here. I'm going to draw coordinate axes here. And I'm going to start by just graphing the function b1 of x. So b1 of x again equals x minus 1/2. So this is just a straight line with a slope of 1 and a y-intercept of y equals negative 1/2. And then if I wanted to graph the periodic Bernoulli polynomial b1 of the fractional part of x, that would just equal the fractional part of x minus 1/2. And we actually already saw what that graph looks like. It's just going to be the section of b1 of x from x equals 0 to x equals 1, repeated infinitely many times to the left and to the right. So when x equals 0, b1 of x equals negative 1/2. But then, as the fractional part of x increases, this line, of course, also goes up until x equals 1. And then the fractional part of x again equals 0. So the y value drops back down to negative 1/2. And that process repeats itself infinitely to the left and to the right. What's going on here? Well, the fractional part of x is itself periodic. It has a period 1. And therefore, any function in the fractional part of x, any polynomial in the fractional part of x, is also going to have a period 1. So if we look at the next Bernoulli polynomial, b2 of x, this is the parabola x squared minus x plus 1/6. The fractional part of x, is just the domain of that function where x lies between 0 and 1. And so b2 of the fractional part of x is just going to be a repeating copy of that parabola on its values for x between 0 and 1, repeated infinitely to the left and to the right. And it's the same story for b3 of x. b3 of x is a cubic, and b3 of the fractional part of x is going to be that section of the cubic where x ranges from 0 to 1, repeated infinitely to the left and to the right. And now the fact that these periodic Bernoulli polynomials keep showing up in our error integrals for the various forms of the Euler MacLaurin summation formula that we've derived is really great news for us, because the periodic Bernoulli polynomials are bounded, which means that even if we can't directly compute the error integral, and often we can't, we can still very often estimate that integral numerically because we have good bounds on the behavior of the periodic Bernoulli polynomial contained in the integration. And I'll do an example at the end of this video where I'll show how that works. But before we do that, I just want to press ahead a bit more with our derivation and show how we can develop the fourth and fifth derivative versions of the Euler MacLaurin summation formula with remainder. And once we've done that, we'll be able to make some more general observations about the Euler MacLaurin summation formula and state this formula in its most general form. So once again, here's our third derivative form of the Euler MacLaurin summation formula. And if we want to refine the formula further, we need to evaluate this error term. Now, just for teaching purposes, I'm going to switch the first and last two terms in parentheses there around. We'll get the same result if we don't do that, but I think it makes the exposition clearer if we do switch them. So we'll do that, and then once again, we'll integrate by parts. So I think at this point we know what to do. We'll make u equal to f triple prime of x, so du is the fourth derivative of f of x dx, and then dv is going to be that periodic Bernoulli polynomial b3 of the fractional part of x, and then v will be the integral of that polynomial, and so we then find that v equals the floor of x plus the fractional part of x squared all over 4 minus 3 times the floor of x plus the fractional part of x cubed all over 6 plus the floor of x plus the fractional part of x to the fourth all over 4. And so now if I rearrange these terms, I have that v equals the floor of x over 4 minus 3 times the floor of x over 6 plus the floor of x over 4 plus these terms that are all terms in the fractional part of x. And so the floor of x terms actually cancel. And so we're left with v being equal to the fractional part of x squared over 4 minus the fractional part of x cubed over 2 plus the fractional part of x to the fourth over 4. Well, that's nice. As we've already seen, we are very happy when v only contains terms in the fractional part of x. And so we have that our integral equals u times v, so f triple prime of x times v. I'm not going to read out that expression again. Evaluated from 1 to n minus the integral from 1 to n of v times du, which is the fourth derivative of f of x dx. But once again, because v only contains terms in the fractional part of x at the integer values, the fractional part of x equals 0, so v equals 0, and that term cancels out. And so we reach this intermediate expression where we find that the integral is equivalent to negative 1/6 times the integral from 1 to n of, open parenthesis, fractional part of x squared over 4 minus fractional part of x cubed over 2 plus fractional part of x to the fourth over 4 close parenthesis times the fourth derivative of f of x dx. And just the same as before, one round of integration by parts isn't sufficient to produce a new form of the EMSF, so we need to do another round of integration by parts. We'll let u equal the fourth derivative of f of x, then du will equal the fifth derivative of f of x dx. And then we'll have that v equals the integral of that expression in parentheses. So I'm not going to read it out again, but we'll have that v equals the floor of x plus the fractional part of x cubed all over 12 minus the floor of x plus the fractional part of x to the fourth all over 8 plus the floor of x plus the fractional part of x to the fifth all over 20. And once again, I'm going to simplify this expression for v by separating out the floor of x terms. So I'm going to have that v equals the floor of x over 12 minus the floor of x over 8 plus the floor of x over 20 plus terms in the fractional part of x cubed, the fractional part of x to the fourth, and the fractional part of x to the fifth that I'm not going to even write out here. And then recall that the floor of x is equal to x minus the fractional part of x. So I'll have that v equals x over 12 minus the fractional part of x over 12 minus x over 8, and then I have a double negative, so plus the fractional part of x over 8, and then plus x over 20 minus the fractional part of x over 20, plus all of those other terms in the fractional part of x cubed, fractional part of x to the fourth, fractional part of x to the fifth. So I can take my fractional part of x terms as well and set those aside. I'm really just focusing on the fact that v equals x over 12 minus x over 8 plus x over 20 plus, again, these other fractional terms. And the point is that my terms in x, my terms in the non-fractional values of x, do not cancel. X over 12 minus x over 8 plus x over 20 unfortunately does not equal 0. Well, what does it equal? Well, it turns out that the common denominator here for these terms is 120, so we have v equals 10x over 120 minus 15x over 120 plus 6x over 120, and that reduces to x over 120. So v equals x over 120 plus all of these fractional terms. And as we've seen already, having a non-fractional term in our expression for v is bad news for us if we want to do this integration, because when we do the integration by parts, our expression u times v, which is evaluated at the endpoints 1 and n, that's not going to cancel if we have a non-fractional term there. And also the other part of the integration by parts, the integral of v du, which becomes our error integral in the new version of the formula, that's going to be larger than we want because we have that non-fractional term. So what can we do to get rid of this x over 120 term? Well, we've seen this already. We need to adjust the integral in some way. And we're going to use the exact same trick that we used before. We're going to add a creative form of 0 inside the integral that will change the integral's form without changing its value. And so again, without changing the value of the integral, I'm going to rewrite the terms inside parentheses as the fractional part of x squared over 4 minus the fractional part of x cubed over 2 plus the fractional part of x to the fourth over 4, and now here's the trick, minus 120 plus 120 close parenthesis. This allows me to split the integral into two pieces, so I have that polynomial expression minus 120 multiplying the fourth derivative of f of x dx. And then I also have plus negative 1/6, remember that's the coefficient out front that gets carried along, times the integral from 1 to n of 1 over 120 times the fourth derivative of f of x dx. Now I'm just going to rearrange those two terms so that the integral is the last term on the right-hand side of this equation. And I just want to simplify the integral a little bit by factoring out a 4 from the denominator in all of those terms. So to do that, I have to multiply that middle term, fractional part of x cubed over 2. I have to multiply that term by 4 over 4. And then when I do that, I can factor out a 4 from all of these terms inside the integral, and I'm left with this integral being equal to negative 1 over 24 times the integral from 1 to n of the fractional part of x squared minus 2 times the fractional part of x cubed plus the fractional part of x to the fourth minus 1 over 30, close parenthesis, times the fourth derivative of f of x dx. And if we turn our attention to the other integral expression on the right-hand side here, the expression negative 1/6 times the integral from 1 to n of 1 over 120 times the fourth derivative of f of x dx, we might notice that we can factor out a 4 from that integral also. And then we'll have negative 1 over 24 times the integral from 1 to n of 1 over 30 times the fourth derivative of f of x dx. But I might as well just pull out that 1 over 30 constant in front as well. So then I'll have negative 1 over 30 times 1 over 24 times the integral from 1 to n of the fourth derivative of f of x dx. But of course, this integral is really easy to evaluate. It's just f triple prime of n minus f triple prime of 1. And so we end up with the integral equaling negative 1 over 30 times f triple prime of n minus f triple prime of 1 all over 24. So evaluating that integral gives us a new correction term in the Euler MacLaurin summation formula. And finally, when we turn our attention back to the error integral, if I just rearrange terms here in parentheses, so I'm going to switch around the fractional part of x to the fourth and the fractional part of x squared, just to put this in a form we might recognize a little bit better, this expression, fractional part of x to the fourth minus 2 times fractional part of x cubed plus fractional part of x squared minus 1 over 30, this is just b4 of the fractional part of x, which is the fourth periodic Bernoulli polynomial. So I'll put a box around this formula because we've just derived the fourth derivative form of the Euler MacLaurin summation formula with remainder term. Now, if we were to evaluate that error integral further by, of course, performing integration by parts, well, I won't show you the calculation because I think at this point you understand how it would be done. We end up with the summation of the values of the function equaling the same first four terms plus a new integral, plus 1 over 120 times the integral from 1 to n of, open parenthesis, fractional part of x to the fifth minus 5 over 2 times the fractional part of x to the fourth plus 5 over 3 times the fractional part of x cubed minus 1/6 times the fractional part of x, close parenthesis, times the fifth derivative of f of x dx. And this polynomial expression in the fractional part of x is, of course, b sub 5 of the fractional part of x, the fifth periodic Bernoulli polynomial. And this equation is, you guessed it, the fifth derivative form of the Euler MacLaurin summation formula with remainder. So now we've derived enough different versions of the EMSF with remainder term that I think we can spot some general patterns. So for the sake of comparison, let's list out the various forms of the EMSF with remainder that we've derived so far. We have the first derivative form. This is the one that says that the summation of the values of f on the integers k equals 1 to n is equal to the integral from 1 to n of f of x dx plus the average value of f at the endpoints, that is to say f of n plus f of 1 all over 2, plus the integral from 1 to n of, open parenthesis, fractional part of x minus a half, close parenthesis, times f prime of x dx. Okay, that's the first derivative version. And then our second derivative version of the EMSF says that that summation equals the same thing for the first two terms, plus 1/6 times f prime of n minus f prime of 1 all over 2, minus 1/2 times the integral from 1 to n, and here I'll just say the second periodic Bernoulli polynomial times f double prime of x dx. And then the pattern continues into our third derivative form of the EMSF, where we have that the summation is equal to the first three terms of the second derivative version plus a new error integral, plus 1/6 times the integral from 1 to n of the third periodic Bernoulli polynomial times f triple prime of x dx. Our fourth derivative form of the EMSF has the same first three terms as the second and third derivative forms, and then we have a minus 1 over 30 times f triple prime of n minus f triple prime of 1 all over 24. And actually, let me see if I can fit that term on the same line as the others there. Yes, that's good. And then minus 1 over 24 times the integral from 1 to n of the fourth periodic Bernoulli polynomial times f quadruple prime of x dx. Well, since we know that within the error integral for each of these versions of the EMSF, the polynomial expression in fractional part of x is always a periodic Bernoulli polynomial, and these periodic Bernoulli polynomials contain more and more terms as we go. Just to be more concise, I'm going to write them all as b sub 1 a fractional part of x, b sub 2 a fractional part of x, b sub 3 a fractional part of x, and so on. The next thing we might notice when looking at these formulas is that the constant that's multiplying f prime of n minus f prime of 1 over 2 in formulas 2, 3, and 4, we might recognize that constant to actually itself be a Bernoulli number. That's b sub 2, lowercase b sub 2. Similarly, the constant multiplying f triple prime of n minus f triple prime of 1 all over 24, that's in formula 4 there, that is the Bernoulli number lowercase b sub 4. So just by looking at the first 4 versions of the EMSF, another pattern involving Bernoulli numbers is emerging here. Now I think I have just enough space to include the 5th derivative version of the EMSF with remainder, so I'll write that there. This is the formula that says the sum of the values of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus f of n plus f of 1 all over 2 plus b sub 2, the second Bernoulli number, times f prime of n minus f prime of 1 all over 2 plus b sub 4 times f triple prime of n minus f triple prime of 1 all over 24 plus 1 over 120 times the integral from 1 to n of the 5th periodic Bernoulli polynomial times the 5th derivative of f of x dx. And for the purposes of pattern recognition, having the 5th derivative version of the EMSF written there is very helpful, because when we look at the denominators across that equation, we see 2, 24, 120. And actually looking back at the 4th derivative form, we see 2 and 24, and in the 3rd derivative form, we see 2 and 6. What do those numbers all have in common? Well, those numbers are all factorials. So let me replace all of those numbers with their equivalent factorial expressions. And I have just one more pattern that I want to point out here, which is that the signs of the constants in front of the error integrals in all of these different versions of the EMSF, the signs always alternate. So in the first derivative version, we have a plus sign in front of the error integral. In the second derivative version, we have minus 1 over 2 factorial times the error integral. In the third derivative version, we have plus 1 over 3 factorial times the error integral, and so on. So I'll just bring the 5th derivative form of the EMSF with remainder up to the top line there. And then with all of these patterns that we've been able to discern, we should be able to guess what the 6th derivative form of the EMSF would be. It would say that the sum from k equals 1 to n of f of k equals the integral from 1 to n of f of x dx plus f of n plus f of 1 all over 2 plus the second Bernoulli number b sub 2 times f prime of n minus f prime of 1 all over 2 factorial plus lowercase b sub 4 times f triple prime of n minus f triple prime of 1 all over 4 factorial plus b sub 6 times the 5th derivative of f of x evaluated at n minus the 5th derivative of f of x evaluated at 1 all over 6 factorial minus 1 over 6 factorial times the integral from 1 to n of capital B sub 6 of the fractional part of x, that's the 6th periodic Bernoulli polynomial, times the 6th derivative of f of x dx. And while we're at it, we might also infer the 7th derivative form of the EMSF with remainder. We might have noticed that the odd derivative versions of the EMSF with remainder keep all of the correction terms of the previous even derivative version of the EMSF that preceded it. So the 7th derivative form of the EMSF has all the same terms as the 6th derivative form, except for the error integral, which in this case will be plus 1 over 7 factorial times the integral from 1 to n of capital B sub 7 of the fractional part of x times the 7th derivative of f of x dx. And now we're ready to generalize our formula. So we're going to write that the summation of the values of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus f of n plus f of 1 all over 2 plus, and now I'm going to group all of these correction terms together as one sum, and I'll index it from m equals 1 to the value floor of r over 2. You'll see why we need that in a moment. And so this is the sum of our even subscripted Bernoulli numbers, so b sub 2m times the 2m minus 1 derivative of f of n minus the 2m minus 1 derivative of f of 1 all over 2m factorial. And you can just compare that formula to the correction terms in what I have up there, the 7th derivative form of the EMSF, to see that that accurately captures the pattern. And again, I'm letting the index of this summation range from m equals 1 to m equals the floor of r over 2. Now, why do I need to use the floor function for this sum? Well, that's to capture the fact that the odd derivative forms of the EMSF have all the same correction terms as the even derivative form of the EMSF that precedes them. We just saw this with the 7th derivative form of the EMSF that has all the same correction terms as the 6th derivative form. So for example, if we let r equal 6, then the floor of r over 2 will just be the floor of 3, which equals 3, and we'll get all of the correction terms that we expect in the 6th derivative form of the EMSF. But then we want those same terms also to be in the 7th derivative form. So if we let r equal 7 there, then the floor of 7 over 2 is the floor of 3.5, which also equals 3. So we get all the same correction terms for the 7th derivative form as we had for the 6th derivative form. That's pretty neat. And now all that's left in our formula is the remainder integral, which, as we said, alternates signs. So that's going to be plus, open parenthesis, -1, close parenthesis, to the r plus 1 times 1 over r factorial times the integral from 1 to n of capital B sub r of the fractional part of x, that's the rth periodic Bernoulli polynomial, times the rth derivative of f of x dx. Well, isn't that just an amazingly beautiful formula? But in fact, there's one more thing we can do to make our summation formula even more general and even more versatile. You see, our framing the derivation of this formula as the summation of the values of f of k from k equals 1 to k equals n was somewhat arbitrary. And so, because we could actually begin the summation anywhere, I'm going to replace the value 1 in the formula with the variable I. This isn't I the imaginary number, it's just some integer I. And writing the formula in this most general way expresses the fact that we're summing the values of f of k on the integers from our choice of integer I to our choice of integer n. Well, we've spent a lot of time in this video deriving the Euler MacLaurin summation formula with remainder. Now it's time to use it. So we're going to use the EMSF with remainder to approximate the limit as n approaches infinity of the summation of the function 1 over k from k equals 1 to n minus the natural logarithm of n. And this constant is very famous in mathematics. It's called the Euler-Mascheroni Constant. Euler was the one who initially discovered it, and then the Italian mathematician Mascheroni computed the constant to more decimal places than anybody had done before. So some people just call it Euler's constant. I'm going to give Mascheroni some of the credit as well. And usually the constant is denoted by the lowercase Greek letter gamma. Okay, well, before we even compute this constant gamma, let's confirm that it really exists. And here, conveniently, we can return to our setup for how we derived the EMSF to begin with. So I'll ask you to recall, if we have a function f of x that is positive, meaning f of x is greater than 0 for all x, and always decreasing, we can construct the following picture. Here I'll just draw f of x in quadrant 1, but the main point here is that it's always positive and always decreasing. Now I'll just march out some integer values for x on the x-axis here, so 1, 2, 3, 4, ... all the way up to n minus 1, and then up till n. And we've already seen that the discrete summation of the values of f of x, so the summation from k equals 1 to n minus 1 of f of k, minus the integral from 1 to n of f of x dx, can be represented geometrically by the sum total of the areas of the curvilinear pieces sitting above f of x, which we called d sub n. Now I want to make the observation, which is that d sub n, the sum total area of all those curvilinear pieces up to n, is less than the value of f of 1. And how do we know that? Well, we know that because by virtue of the fact that f is continually decreasing, we can just translate all of these pieces of d sub n all the way over to the left with no overlapping, and we see that their area fits inside the rectangle whose area equals f of 1, right? That rectangle has base of 1 and height of f of 1. I also note that if we were to add the area of the next curvilinear piece above f of x, and I'll call that sum total d sub n plus 1, then we have that d sub n must be strictly less than d sub n plus 1, and d sub n plus 1 also has to be less than f of 1, because again, we can translate that additional curvilinear piece all the way over to the left, and without overlapping, it also fits inside the rectangle whose area is f of 1. So we can keep letting n increase and consider the sequence of all of these d sub n's, and we see that they can all fit inside f of 1. So therefore, d sub n is increasing but bounded above by f of 1. Therefore, we can say that the limit as n approaches infinity of d sub n must exist. Now, whatever that limit happens to be, it's going to be a constant that's determined by our function. So we'll call this limit c of f. It's the constant for the function in question. And again, we note because our function is always positive and decreasing, and because of the way that we defined this limit, c of f is always going to be less than f of 1. And let's further observe that the difference between c of f and d sub n, remember c of f is the area of all the curvilinear pieces as n approaches infinity, and d of n is just the area of the curvilinear pieces up to some fixed value n. Well, the difference between that limit and d sub n equals, well, we can visualize it geometrically. That difference would just be the total area of all the curvilinear triangles above f of x from n to infinity. So I'll highlight the curvilinear triangles representing that difference in yellow. And just like we were able to translate the rectangles outlined in blue all the way over to the left to show that their sum total is less than the value f of 1, we can play the same game with these yellow outlined curvilinear triangles that sit above f of n and go all the way to infinity. All of those triangles could be translated to the left, and they all fit inside that rectangle whose area equals f of n. And so the difference between c of f and d of n, c of f minus d of n, must be less than f of n. And because our limit c of f is by definition greater than d sub n, then that difference must be positive. So we can write c of f minus d sub n is greater than 0 and less than f of n. Now, it might already seem like I'm throwing a lot of terminology at you, but it will really help for us getting this proof done. So I'm going to define one more term. We'll define e sub f of n to be equal to f of n minus, open parenthesis, c of f minus d sub n, close parenthesis. Okay, so that's the last term that we're going to need here to do this proof. Now, because we already showed that c of f minus d sub n is greater than 0 and also less than f of n, we can conclude immediately that e sub f of n is both a positive quantity. We know that because f of n is positive and we're subtracting something from it that's less than it, so e sub f of n is still positive, but e sub f of n is also going to be less than f of n because by definition, e sub f of n is equal to f of n minus, open parenthesis, c of f minus d sub n, close parenthesis. So I'll move all of those facts to the top line here, and now we're ready to do our proof. We're ready to prove that the Euler-Mascheroni constant gamma really exists. So based on this diagram, we can write that the sum of the values of f of k from k equals 1 to n minus 1 is equal to the integral from 1 to n of f of x dx plus d sub n. And that just comes from our definition of d sub n. We defined d sub n to be the difference between the discrete summation of f of k from k equals 1 to n minus 1 and the integral of f of x from 1 to n. Now let's add f of n to both sides of this equation. When we do that, we have on the left-hand side now the summation from k equals 1 to n, and on the right-hand side, I'm just going to switch the orders of the terms. So we'll have the integral plus f of n plus d sub n. But recall that we defined e sub f of n to be equal to f of n minus, open parenthesis, c of f minus d sub n, close parenthesis. So I'm just going to apply the negative sign there, and we have e sub f of n equals f of n plus d sub n minus c of f. Then moving c of f over to the left-hand side of this equation, we have e sub f of n plus c of f equals f of n plus d sub n. But that expression, f of n plus d sub n, that matches what we have in the equation at the top, connecting our discrete summation to our integral. So I can substitute it in. And so we can write the summation of f of k from k equals 1 to n equals the integral from 1 to n of f of x dx plus e sub f of n plus c of f. And now something wonderful happens. Let's see what happens when we let n tend towards infinity. Well, because we know that f of x is always positive, always greater than 0, but also always decreasing, we know that the limit as n approaches infinity of f of x equals 0. But also recall from the inequalities we derived above, they're on the top line there, that e sub f of n is sandwiched between 0 and f of n by the squeeze theorem. As we let n tend towards infinity, e sub f of n must also go to 0. And so, taking the limit on both sides of the equation as n approaches infinity, the e sub f of n term has to cancel out. And we get that the sum of f of k from k equals 1 to infinity equals the integral from 1 to infinity of f of x dx plus c of f. Now, so far, I've framed the arguments of this proof in terms of some abstract function, f of x, which I described as being always positive and always decreasing. But for the purposes of our proof, I'm really interested in one specific function that has those properties, the function f of x equals 1 over x. So we'll let f of x equal 1 over x, and then we'll write the limit as n approaches infinity of the sum from k equals 1 to n of 1 over k equals the limit as n approaches infinity of the integral from 1 to n of 1 over x dx. And now in place of c of f, remember c of f is just a constant for some general abstract function, but here our function is 1 over x. In place of c of f, I'm going to write gamma. But now the integral of 1 over x dx, of course, is just the log of x, so I can rewrite the right-hand side as the limit as n approaches infinity of, now here's our definite integral, open parenthesis, log of n minus log of 1, close parenthesis, plus gamma. And now to conclude the proof, the log of 1, of course, equals 0, so rearranging this equation, we have the limit as n approaches infinity of the sum k equals 1 to n of 1 over k minus the log of n equals gamma, the Euler-Mascheroni constant. Well, now that we've derived the Euler MacLaurin summation formula with remainder and proved that the Euler-Mascheroni constant gamma exists, we're now in a position to actually compute gamma to a high level of accuracy using our formula. To do this, let's use the seventh derivative form of the EMSF with remainder. Well, we're going to need a lot of derivatives of f of x equals 1 over x, so let's list them out here. We have f of x equals 1 over x, which equals x to the negative 1. F prime of x, then, by the power rule, equals negative 1 times x to the negative 2. F double prime of x will equal negative 2 times negative 1 times x to the negative 3, which equals 2 factorial times x to the negative 3. F triple prime of x then equals negative 3 times negative 2 times negative 1 times x to the negative 4, which equals negative 3 factorial times x to the negative 4. And now I hope you can see the pattern. The fourth derivative of f of x equals 4 factorial times x to the negative 5. The fifth derivative equals negative 5 factorial times x to the negative 6. The sixth derivative equals 6 factorial times x to the negative 7. And the seventh derivative equals negative 7 factorial times x to the negative 8. Now, for the purposes of the Euler MacLaurin summation formula, we only need f of x and its odd-indexed higher-order derivatives, so I'll group those together and move them to the right-hand side of the screen for reference. And now recall that by the seventh derivative form of the EMSF with a remainder, we have that the sum from k equals 1 to n of f of k equals the integral from 1 to n of f of x dx plus the quantity f of n plus f of 1 all over 2 plus b sub 2, that's the second Bernoulli number, times the quantity f prime of n minus f prime of 1 all over 2 factorial, plus b sub 4 times f triple prime of n minus f triple prime of 1 all over 4 factorial, plus b sub 6 times the fifth derivative of f evaluated at n minus the fifth derivative of f evaluated at 1 all over 6 factorial, plus 1 over 7 factorial times the integral from 1 to n of the seventh periodic Bernoulli polynomial of x times the seventh derivative of f of x dx. So that's our general formula. Now let's use it for our function f of x equals 1 over x. So then we'll have that the summation from k equals 1 to n of 1 over k equals the integral from 1 to n of 1 over x dx. Well, we already saw that the integral of 1 over x is just the log of x, so this will equal the log of x evaluated at the endpoints n and 1, so this will be log of n minus log of 1, but as we already saw, log of 1 just equals 0, so I'll cancel out that term. So we now have that the sum on the left-hand side equals the log of n plus these other correction terms in the remainder term. Now that first correction term, which is sometimes called the trapezoidal correction term, that would just be f of n plus f of 1 over 2. So that's 1 over n plus 1 over 1 all over 2, which equals 1 over 2n plus 1/2. For our next correction term, we make use of the fact that f prime of x equals negative 1 times x to the negative 2, which is negative 1 over x squared. So we get that this correction term equals b sub 2 over 2 factorial times the quantity negative 1 over n squared minus negative 1 over 1 squared. And now because of that double negative, the term in parentheses just equals 1 minus 1 over n squared. For our next correction term, we'll have b sub 4 over 4 factorial times the quantity negative 3 factorial over n to the fourth minus negative 3 factorial over 1 to the fourth. And then applying the double negative to rearrange these terms, this will be 3 factorial over 1 minus 3 factorial over n to the fourth. But now I have a 3 factorial in the numerator of both of those terms in the parenthesis there, and outside the parenthesis I have a 4 factorial in the denominator, so I can cancel out the 3 factorials and I'll end up with a 4 in the denominator, and so I'll have b sub 4 over 4 times the quantity 1 minus 1 over n to the fourth. And a similar pattern applies to the next correction term, where I have b sub 6 over 6 factorial times the quantity negative 5 factorial over n to the sixth minus negative 5 factorial over 1 to the sixth. This will become b sub 6 over 6 times 1 minus 1 over n to the sixth. And now lastly, in our remainder term, I'll substitute in for the seventh derivative of f of x what that derivative actually is. So that's negative 7 factorial over x to the eighth. And so then the 7 factorials cancel in the numerator and the denominator there, and then I'll just bring that negative sign out in front, and so the remainder term becomes minus the integral from 1 to n of the seventh periodic Bernoulli polynomial in x times 1 over x to the eighth dx. Great, so now I'll just get rid of my list of higher order derivatives of f of x equals 1 over x since we don't need them anymore, and I'll move these terms over to the right to make a little bit more room. Now, remember, what we're after is the difference between the sum from k equals 1 to n of the function 1 over k and log of n. In other words, we're interested in the difference between the nth partial sum of the harmonic series and log of n. So I'm just going to subtract log of n from both sides of the equation to produce that expression on the left-hand side. And then if we take the limit as n approaches infinity on both sides of this equation, on the right-hand side of the equation, all of the terms that have powers of n in the denominator cancel, and our error integral also is now from 1 to infinity instead of from 1 to n. So now I can just bring together on one line all the terms on the right-hand side that survived cancellation, and of course the terms on the left-hand side, the limit as n approaches infinity of the nth partial sum of the harmonic series minus log of n, that of course is just the Euler-Mascheroni constant gamma. Now we might think naively that we can just compute gamma directly, but if we look at that error integral, the integral from 1 to infinity of the seventh periodic Bernoulli polynomial times 1 over x to the eighth dx, I'm not aware of any really good way to compute that integral. But in the end, we're not really interested in the value of that integral per se. We're interested in it insofar as it will bound the error for us, but we're really looking at gamma. And so we need to figure out a way to approximate gamma here, making use of the Euler MacLaurin summation formula. And the idea here is now to compare the above equation, which is really the limiting case where we let n go to infinity, with a simpler finite case where we'll just set n equal to 10. And so if we set n equal to 10 in the Euler MacLaurin summation formula for our function f of x equals 1 over x, I can just plug in 10 for n in all the places that n showed up in that formula. So I've just sort of copied and pasted the formula in that we derived before, but now I'm subbing in the number 10 for n. So we have two equations here. Our top equation is our formula for gamma, where we let n tend towards infinity in the Euler MacLaurin summation formula. And our second equation is the Euler MacLaurin summation formula, where we've let n equal 10. And now I'm going to just simplify the right-hand side of that equation by distributing the Bernoulli numbers across the terms that they're multiplying. So I'm going to get, for example, b sub 2 over 2 minus b sub 2 over 2 times 1 over 10 squared. Then I'll get plus b sub 4 over 4 minus b sub 4 over 4 times 1 over 10 to the fourth, and so on. I'm also going to subtract the log of 10 from both sides of that equation. So on the left-hand side, I'll now have the sum from k equals 1 to 10 of 1 over k minus log of 10 equals all of these correction terms minus the error integral. And now this is really the key step. We're going to subtract the second equation from the first equation. So when we do that, we have gamma minus, open parenthesis, the sum from k equals 1 to 10 of 1 over k, minus log 10, close parenthesis, equals. And now all of these terms cancel. 1/2, b sub 2 over 2, b sub 4 over 4, b sub 6 over 6. Those terms all cancel out. And then on the right-hand side, we have minus 1 over 2 times 10, so minus 1 over 20, and then plus b sub 2 over 2 times 10 squared, so plus b sub 2 over 200, then plus b sub 4 over 40,000, and then plus b sub 6 over 6 million. And now we just have to take the difference of these two integral expressions. So in the top equation, we have minus the integral from 1 to infinity of the seventh periodic Bernoulli polynomial times 1 over x to the 8th dx. And in the bottom equation, we have a double negative. We have minus negative integral from 1 to 10 of that same expression. And so when we do the subtraction, we end up with minus the integral from 10 to infinity of the seventh periodic Bernoulli polynomial times 1 over x to the 8th dx. And now we're ready to actually compute gamma. So I'm going to plug in the actual values for the Bernoulli numbers in this formula. B sub 2 is 1/6, B sub 4 is negative 1 over 30, and B sub 6 is 1 over 42. And I can manually compute the 10th partial sum of the harmonic series. That's also called the 10th harmonic number, h sub 10. That just equals 1 over 1 plus 1 over 2 plus 1 over 3, etc., all the way up to plus 1 over 10. And that equals about 2.92896825381. I can also compute directly the logarithm of 10, for example, by using the Taylor series for the logarithm, and we have that the log of 10 is equal to about 2.30258509299. Now in our formula, we're subtracting the logarithm of 10 from the 10th harmonic number. So when we do that subtraction, h sub 10 minus log of 10, we get 0.626383316. So let's write that result into our formula there, replacing h sub 10 minus log 10. And now I just want to turn our correction terms into decimals. So minus 1 over 20 becomes minus 0.05. And now before I do 1 over 1200, let me just move those terms down to make some room. Okay, so 1 over 1200 would be about equal to, we're going to 8 decimal places here, 0.000833. And then our next term, negative 1 over 30 times 1 over 40,000, to 8 decimal places, that would be negative 0.0000083. And then we can ignore the next term after that. That's too small to even influence the 7th digit in our sum. And then we're finally left with our error integral. And as I mentioned before, this is difficult to compute directly, but the next best thing we can do is bound this integral. And so we're really asking the question, how big could this term get? And this is where the fact that we have a periodic Bernoulli polynomial inside the integrand there is such great news for us, because we know that the periodic Bernoulli polynomials are bounded. More concretely, we know, and I proved this in my previous video on the Bernoulli polynomials, that the absolute value of the 7th periodic Bernoulli polynomial must be less than or equal to 7 times the 6th Bernoulli number, b sub 6. That is, it must be less than or equal to 7 times 1 over 42, or less than or equal to 1/6. And so because I know that the absolute value of the 7th periodic Bernoulli polynomial is bounded, it's less than or equal to 1/6, I know then that the integral expression, integral from 10 to infinity, of the 7th periodic Bernoulli polynomial times 1 over x to the 8th dx, I know that that integral, its absolute value, its magnitude, must be less than or equal to the integral from 10 to infinity of 1/6 times 1 over x to the 8th dx. But that's an integral I can compute very easily. First of all, I can just pull out the constant 1/6 in front of the integral. So now I'm just doing 1/6 times the integral from 10 to infinity of x to the negative 8 dx. Well, that's just going to be equal to 1/6 times x to the negative 7 over negative 7, evaluated at the endpoints 10 and the limit as we approach infinity. So this is going to equal the limit as m approaches infinity of negative 1 over 42 times 1 over m to the 7th plus 1 over 42 times 1 over 10 to the 7th. Well, that expression limit is m approaches infinity of negative 1 over 42 times 1 over m to the 7th. That term just goes to 0. And I'm left with this integral equaling 1 over 42 times 10 to the 7th. So we have that this error integral is bounded and less than or equal to 1 over 42 times 10 to the 7th. Well, that value is also too small to even influence the 7th decimal place here in the computation. And so that error integral also drops out of the computation for gamma if we want to approximate gamma to 8 decimal places. And so even without directly computing the error integral, by making this powerful argument about how the periodic Bernoulli polynomials are bounded, we're able to at least show that our error has to be within a very, very small margin here. And so to at least 8 decimal places, we have that gamma is about equal to 0.6263816 minus 0.05 plus 0.0008333 minus 0.0000083. So in other words, our first term there is the 10th harmonic number minus log of 10. Well, that number, 0.6263816, is a pretty poor approximation for gamma. It's not even accurate to 1 decimal place. But with just 3 correction terms from the Euler MacLaurin summation formula, and we saw actually that the 4th correction term was too small to make a difference here, and with our estimation of the error integral confirming for us that we're going to be accurate to 8 decimal places, we have that gamma is approximately equal to 0.57721566. Well, that's it for today. I know this was a rather long video, but I think we accomplished a lot. I hope you enjoyed it, and if you did, please like or subscribe to my channel. Thanks again.